Hello to all of you. I'm Ophélie Renaud, a PhD student in SAREN, and I'm going to present you SCAPE, an hardware-aware clustering of Dataflow for tunable scheduling complexity, work supported by the IETR, and presented at the workshop Vaader. Parallelizing a program consists in exploiting all the resources of an architecture in an optimized way. The design of a program starts with a draw, and what should contain this draw? It should reveal the dependency between tasks, make visible any missing details. And that's why a lot of researchers use the Dataflow model to describe efficient application that take benefit of every available resources. And what is Dataflow? So, well, it's a graph composed of actors that represent computation and connected to each other via iterated axes that represent the buffer FIFO, and on which we transit data tokens. So there is many types of data flow, and one of them is a synchronous data flow. So well, there is an integer on the ports of actor that correspond to the rate of tokens consumed and rate of token produced by this actor. And an extension of this model is PSDF for parameterized and interface synchronous data flow. So the parameters are node associated to a scalar value that allow to specify a rate by an expression. And the model integrates the hierarchy. So an actor, instead of being specified by C code, is specified by a subgraph. And interface are nodes that allow to the transfer of tokens between graphs. And a reduction of the model is the SRDAC for single rate directed acyclic graph. And it's a graph on which on each FIFO the produced token and the consumed tokens are equals, and the transformation does not contain cycles. And the model has a lot of advantages, and the main first one is that it expresses several types of parallelism. For example, task parallelism is actor A and actor B can be executed simultaneously on two processing elements. Data parallelism is if there is enough data tokens, the input ports of the actor C, two instances of this actor can be executed simultaneously on two processing elements. And pipelining and internal parallelism are not studied in this presentation. And the second main advantage is that it is necessary to represent an application only once to be portable on any type of architecture. So for all these reasons that the paper uses this model. So in order to achieve the efficiency of the data flow, three parts are involved: the input, process, and output. So we focus on output that follows the algorithm architecture education methodology. So then the process consists in solving resource allocation, and we focus on a static one, that is during the compilation. And resource allocation involved in two steps: mapping and scheduling. Mapping consists in distributing actor on a processing element, and scheduling consists in ordering this element on the processing element. Then the output is parallel generated code, So the contribution of the paper concerns the process part and the output part. And I first talk about the process part. So the classic static scheming process involved four steps: flattening, SRI transformation, mapping, and scheduling. So flattening consists in putting all the actors on the same level. So by replacing the hierarchical actor by their contents. Then the SRDAG will reveal the parallelism by highlighting the minimal number of values of each actor to return the graph back to its original state, and it's a value given by the computation of a repetition vector. Here the values are written in red here, and so we see the translation here, and it highlights also the required special actor that are able to gather or distribute token on a different instance. Then the process is able to map and schedule each element of the transform graph individually. So the problem that arises is twofold. First, the classic static scheming process time increase as the application and the architecture complexity increase. And the second is due to the fact that mapping opportunities is limited to the number of processing elements, it is not necessary to describe an application with a degree of parallelism that exceeds the one of the targets. So, in order to illustrate the problem, here we consider the SqueezeNet neural network. So it's a SDF graph containing 70 actors. Its degree of parallelism is up to 1,000. Its SRI transformation contains more than 5,000 actors. And the analysis time, that is the time that the tool takes to map, schedule, and generate code. On 4 processing elements is estimated to 56 days. That is a lot. So the problem that arises is how to reduce the complexity of a program without compromising its parallelism. So here we have 2 objectives: reduce analysis time, and we take as a criterion of success side of the SRI, and then not to compromise the latency by keeping the parallelism. So now the contribution. The clustering transformation will reduce the complexity of the graph and happen just before the flattening process and involved in the steps. First, by identifying a particular pattern of actor, then generate a subgraph that contains these the identified actors, then compute the schedule of the subgraph, and then generate the code associated to the subgraph, and then replace the behavior of the hierarchical actor by the newly created code. And I will detail the 2 first steps next slide. So the goal of the first step is to reduce the SRI and reduce the analysis time by identifying 2 patterns. The first one is a unique repetition point. So it's at least 2 sequential actors with, to make it simple, the same repetition vector. So the method cluster it in one single actor in order to have an SRI of 1 actor instead of 3 times 8, 24. And the second pattern is a single repetition vector. So it's an actor with a repetition vector greater than the number of processing elements that does not belong URC unique repetition candidates. So the idea is the same. Cluster it in one actor instead of 16 in terms of size of SRDAG. So here we see that we drastically reduce the size of the SRDAG, but consequently make the application sequential. So the goal of the second step is to retrieve the just losing algorithm by creating a cluster with a repetition vector that match with the number of processing elements, and also called scaling. So here, for example, if we consider an architecture of 4 processing elements, we will make it iterate the hash collector 4 times, and it contains twice in order to have 4 times 2 equal to 1 times 8, and we try the same output of the application. So here, to illustrate in this application, without clustering, we obtain a SRDAG of 53 actors. And with the method, we obtain a reduced SRDAG of 13 actors, and the latency is the same. So now I will talk about the code generated for the cluster. So the code generation for the classic method involved in a specified file for each processing event, and this file contains a scheduled function call that corresponds to the actor firing. And the generated code for the cluster corresponds to a nested function call corresponding to the cluster, and they contain a for loop that represents the firing instance of the contents. And now to illustrate the method, here we consider the stereo application, that is an image processing application that taking input image or video and generate an output def map. So the SDF model contains various forms of parallelism, various firing instance, and also the hierarchy. So I will compare on this graph comparison without clustering. So we have a SRDAG of 187 actors to 3 clustering configuration. The level 3 clustering configuration consists in grouping, clustering the entire graph into one single actor. So it will the SRDAG is 1, and it will make the application sequential. The level 2 clustering configuration consists in clustering the entire hierarchy and then identifying the pattern on the top level. Here we see various size of SRDAG that correspond to the scaling, but also reduce compared to the configuration without clustering. And then the level 1 clustering configuration consists in identifying a pattern only on the hierarchy. So we have also reduced SRDAG. So here are the results. In red, the configuration without clustering, and the different shade of blue, the different clustering configuration. So we see that in terms of analysis time, all clustering configuration are faster than the configuration without clustering. We see also that the level 3 clustering configuration remain fast and constant whatever the number of processing elements, but also is sequential in terms of latency. The complexity of the level 0 configuration provides the best mapping of alternatives, so that's why the red curve provides the best latency. The latency of the level 1 clustering configuration is slightly deteriorated for a significant improvement in this time. That's why the curve here are the same, are close. So here I compare 3 image processing, 0 that we have just seen before, stabilization and SqueezeNet. And here the value, I compare the best clustering configuration to the configuration without clustering. So in green correspond to speed up and red correspond to speed down. So we see that there is of green value, but I will talk about the red values first. So we observe that for a very small application, the clustering process time is greater than the analysis time gains. So it's not relevant to apply the method on really small application. And then why the speed up are really important here is the more complex the application, the greater the analysis time gains, and the less the difference between an execution time of the application. So to conclude, scaling up of cluster of actor and processing element provide a set of clustering configuration with different level of granularities. Provide a trade-off between analysis time and is implemented into Prism and available on GitHub. And future work include identifying and clustering more complex pattern on each hierarchical level, and in extending clustering to other types of algorithm. Thank you.
Thank you. Question time.
Did you measure the latency as theoretically computed by your analysis, or was it run on a third party? Is it raised from Prism, or is it just
the value on the presented are measured by a Prism.
Clustering, one of the reasons of clustering is not really focus, it's to make sure that we match memory, which can have a lot of influence. Yeah. It would be interesting to run those things to see far are we from the truth.
Yeah.
Question. A lot of this work seems to be motivated by the fact that single rate DAGs explode the size of the model, right?
Yeah.
Aren't there any analysis or scheduling algorithms that work on SDF directly?
Should answer maybe.
Maybe.
Yes, yes, there is. We worked on it a few years ago during the PhD of Florian Arestier, and he worked on the possibility to do the whole scheduling based on the SDF graph. The basic idea is, the first question is, why do we go to the single rate version? The single rate exposes all the parallelism, and it exposes all the producers and consumers of memory objects that are transiting and tokens that are transiting on the network. So it is very convenient to use the single rate graph because we can identify all the separate actors and all the separate firings of their actors and how they access memory. So this is why we go to the single rate graph. But the work of Florian Arestier from 2-3 years ago worked on a way to model the same data based on the SDF graph and the set of equations. So basically, each time you fire an actor, you can compute on the fly where the data is supposed to come from and which actor, which firing of another actor has produced the corresponding data. And so this helps to speed up a lot the mapping and scheduling. This was done in the context of dynamic scheduling, whereas Ophélie is working on the offline problem. So these are two different approaches to tackle, let's say, the same problem, more or less. But yeah, it has been done before. It works.
Okay. All right. Because in my master work, I did a simple pseudo core scheduler, and I didn't go to single rates. I just used the heuristic.
Yeah, but how did you allocate the FIFOs, the memory? Did you allocate objects that behaves like a FIFO?
No, I pre-compute the exact location of each
Okay,
token as I simulate, right?
you simulate, yeah.
I simulate, yes.
This is
That would be to add to the answer. You can either build the SI graph, or you can simulate.
Okay.
And
That's
one is going in memory where you spread everything, and the other one is going somewhere in time because you go through all the different points of your graph. So if you keep your granularity, if you don't cluster in some way, it's just two faces of similar problem, two different approaches of similar problem.
Okay.
any other question? Go ahead.
In terms of state of the art, did you look at how you could compare to clustering or other clustering in Dataflow? Just to keep it in Dataflow, not in general.
For the result, no.
That would mean implementing, so I'm pretty sure you did, but did you look at what was done in other?
But on the state of the art, they mainly focus on reducing the size of the SRD and the complexity of the graph, and they didn't really look at the preserve the polymorphism. So
we have a few people online, so if you want to ask a question, you can just open your microphone and ask a question.
Yeah, then I have a question.
I was waiting for.
It's about memory. So I'm a bit surprised, but did you made an evaluation of the memory footprint when you cluster the task or not?
For this paper, no, but after yes, the cluster FIFO sizing. The cluster use FIFO sizing for memory. So compared to some if you use a rough heuristic from a prism, sometimes clustering gains in terms of memory because of the FIFO sizing.
So there is no clear relation. I mean, when you cluster, maybe the memory footprint increase or decrease. No, it's not always the case.
I'm not really compared to a lot of RC, so I can't answer.
No, but even in your work, I mean, compared to, so you said you have 4 levels, for example.
The memory is quite the same without clustering.
Okay.
It's
Okay.
difficult. It's a bit difficult to answer the question because we did not study it in detail yet. And so basically, as Ophélie mentioned, so inside the clusters, this is more or less FIFO sizing that is used. But to have a complete study, we will need to integrate the memory allocated for the clusters in the memory optimization process of Prism. So at the moment, part of the memory is allocated inside the clusters in the stack when the cluster is allocated. And if the stack of inside the cluster is too big, then we need to allocate the memory in the shared memory of the system, basically. This is a bit hybrid, and this has not been studied yet into detail. And so, yeah, sometimes we know that we gain some memory because FIFO sizing might be more efficient than memory merging. But sometimes we may lose also a bit of memory, but we would need to study it in more detail and add more code before we can provide a definitive answer.
Yeah, I think it's a complicated question.
We have a question from Sébastien Renaud.
Oui, bonjour, merci. Thank you for the presentation. I hope that you hear me well. One question for me, I missed the beginning of the presentation about the assumption of the targeted platform. The PE processing elements that you consider, are there processing elements from a GPU, or what kind of platform do you consider, especially about the communication aspect between the processing elements?
We consider homogeneous architecture.
Okay.
Yeah.
And what about the interconnection between the processing element? Is it a shared memory?
With a shared memory, yes. So
it seems to me that you neglect the influence of the communication in your prediction.
Yes, but because we are in a shared memory, I assume that the transfer is the data transfer time is identical.
Okay, it is identical, but you can have contention to when this processing element access to the shared memory. So the things I would think that you could have situation depending on the way you cluster. You should have more or less contention appearing.
Yeah. I think this study will be a future work to into account the architecture in terms of data transfer time to cluster or not.
I may add something. Indeed, we did not take it into account yet, but I'm not sure the effect would be negative. On the contrary, when you cluster the actors, basically you augment also the data locality, because then you have a string of actors or a series of sequential actors where you have a guarantee that the scheduler won't try to schedule them on different cores and add a communication in between. So it's true that it should be taken into account when clustering, but the effect probably would be in favor of the clustering. If we can guarantee that we obtain a directed acyclic graph when we did not sacrifice the parallelism of the application, it means that we kept more or less the same parallelism. We augmented the data locality of the actors that will be scheduled. So this should be in favor of what we are doing, but this needs to be measured also.
Okay, okay, thanks.
Any other question?
Last one, maybe.
Go ahead.
Actually, maybe it was a question also of Michael, I'm not sure, about the latency you measure.
Yeah.
You can come back to the slide.
The value presented come from the frozen
Yeah, no, but it's not the, so I don't remember, it was slide 17 maybe. No, okay, 19. Right. So for the latency, it's either the same or below. But it's never better.
No, I can't with the presented clustering.
Ah, yes. No.
Faster than the.
No, yeah, okay. No, sorry. No. Okay, I understand.
Existing poison.
Yeah, okay. Well, sorry.